Hi. Good afternoon, or evening, or whatever time of day it is for you. So this is going to be one of our recorded lectures for phonetics. In this part, I'm going to go through the problems from last time, so at least you all did get the chance to work on these in class. So I'm going to go through and show you how to work these problems. So it's definitely advisable that you try these all on your own. So maybe you only got to do one in class. I would suggest doing all of them, see how they go. If you're really stuck, then at least if you gave it a shot, then you can try out or you can listen to how I would do this. I will say that some of these are a little bit difficult, especially number 2. So you may not actually, I think you certainly wouldn't encounter ones like number 2, for example, on an exam, but you could see something like this on homework assignments or something like that. I'm actually going to start with number 1, even though we did talk about that in class, just to be thorough. Yeah, so I'll just go through all 4 of these. So the first one, a particular K, has initial volume 3,040 centimeters cubed, and the second volume there, 2,990 cubic centimeters at sea level. So what is the resulting pressure? First of all, I actually gave you the V1 basically. Now you know this is probably a composite of the volume of the lungs plus the volume from the glottis to the constriction. So that's going to be 3,000 for the lungs and 40 for the glottis to the velar constriction. That's going to be important in a minute because we're going to have to do this for P and it's going to look a little bit different. So this first part is really simple. I wrote all the equations up here. We have 5 of them that we have to work with. Well, 4 or 5. You might be able to do the diameter to area on your own. That might be something you've seen before. Anyway, so the question is, what's the resulting pressure? Well, you just use Boyle's law. That's all that this is going to take. So you've already got your V1. Now you might say, okay, well, you didn't give me the P1. Well, we've been assuming that this is going to be atmospheric pressure. So you can go ahead and put 1030 centimeters H2O in there. And you've got V2 was given to you, so that's suggesting basically how much constriction or compression of the lungs you had, and thus how much pressure increase there is following that. So here you get that's the number that I gave you initially, and that would be times the resulting pressure. And so you just simplify this. Type this in your calculator, 3,040 times 1030 divided by 2,990, and that should give you the P2 of 1,047.22, something like that. Don't worry about if I rounded it a little differently from you. The second part, though, what would V2 need to be for a P with the same amount of pressure increase is what I meant to say here. So basically you want to use this P2 for the same equation, but you need to find thus how much constriction would you need for that to get that same amount of pressure behind the P. Now you're still going to use this equation here. You still have 1030 for the initial pressure and you've got P2. Now V1 is going to be different. This is the variable that we have to change here. So instead of 3,040, it's going to be 3,000, the lungs, plus 140, which is the volume from the glottis up to the lip. So that's bigger than the volume from the glottis up to the velar constriction. So the number you want in here for V1 is 3,140. So you end up with this, well, equal to your P2, which is 1,047, times P2, which is what you want. So you solve for P2, and you should get this number that you type into the calculator, 3,140 times 1030 divided by 1047, and that should give you something like 3,088.36 for the new volume needed. And the point I made at the end of class then was that overall you're going to need more constriction than you did for the K. So K, we went from 3,040 to 2,990. That's 50 cubic centimeters of compression. But we have here 3,140 down to 3,088. That's going to be about close to 52 cubic centimeters of compression. So more was needed to get the same amount of pressure increase behind the P. Right. So that was number one. Hopefully that wasn't too bad. That's the kind of thing you're probably more likely to encounter. But we have a lot more equations here, and it's also important to know how to relate these equations, so there are some more complicated problems here. So number two, and again I suggest you try this on your own to see if you get the same thing before I work this out for you. So a particular fricative, say S, it could be produced with a 0.1 centimeter squared cross-sectional channel area. So that's, again, you think about kind of a tube down the tongue, the air goes through that, it hits the back of the teeth. You have that channel, though, that is basically responsible for the frication you end up getting for the S. And so we're saying the area, the cross-sectional area of that tube is 0.1. So if the pressure behind the constriction dropped from 1080 to 1050, what new cross-sectional area would you need to maintain, in order to maintain the same amount of volume velocity? So your first thing you might accidentally do is you might think that I've given you the P1 and the P2, 1080 and 1050, and actually that's not what is being given here. Basically you have two events you have to calculate different things like volume, velocity, etc. for. And of course in both of these you're going to assume 1030 as your P1. So you know this is going to have to go into your volume velocity equation. And I gave you the cross-sectional area, so 0.1 centimeters squared. You already have that, but you're going to need to find U, the particle velocity. To get the volume velocity from this original constriction. So, well, what do you have to do to get that? Use the particle velocity equation I have up here. And remember this P here has to do with the pressure differential. So what was the pressure differential? We get that by thinking about the change in the pressure initially. And so we have two circumstances here. One is that we have initial pressure of 1030 going to 1080. That's our original pressure differential, which is thus a 50 centimeters H2O pressure differential. In time 2, though, you're going from 1030 to 1050, right? And that's a pressure differential of only 30 centimeters H2O. And so these are the important numbers that you're going to plug into this equation, and you're going to get different particle velocities, and that different particle velocities will go into your getting different volume velocities. Of course, you want to keep the volume velocity the same, so that's actually, you can get that with different particle velocities from changing the area of the constriction, and that's what we want to solve for. Anyway, so now we have what we need to get the original volume velocity. So we have this pressure differential of 50 centimeters H2O. Now remember, with this one equation with the constant 412, we need this in millimeters H2O. So you're just going to multiply this by 10. So the actual number you put in here would be 500. So you take the square root of 500, and you times that by 412, our constant, and you should get, or I call it U1 or something like this, 9,212.6, something like that, centimeters per second. I believe it gives you the centimeters, even though you put millimeters in here. Now, you take that and you're ready to find the volume velocity that you need to do this equation. So you take 9,212 times 0.1, and you end up getting a volume velocity of 912, it's just going to be 1/10 of that, 0.26 or something like that, and that's cubic centimeters per second. That's the total volume of air that's coming through this constriction per second. So the point is, we want to keep this volume velocity, but we know that the particle velocity is going to change. We'll find that out in just a minute because we have a different pressure differential. So to maintain this volume velocity, we have to change the area of the constriction. So we find basically U2, and here, so it's 30, the differential for time 2, but actually, of course, we're going to put 300 in here. Nope, 20. I can't do basic subtraction. So 1050 minus 130, it's down to 20, pressure differential of 20. So we're going to put 200, sorry about that, into our equation for the millimeters H2O. And so you take the square root of 200, multiply it by 412, and you should get U2 of something like 5,826 centimeters per second. Now, you're ready to put that into this equation. Now remember, so we're going to find a different area. We have our new U, and then we're actually going to keep the same initial volume velocity because we want to find what the area would need to be to maintain that volume velocity. So you're going to end up, well, it'll be 912.26 equals the second U times the area. So we divide this out, and it should be whatever 912 divided by 5,826 is, and what I get is about an area of 0.156 centimeters squared. So you can see, and that probably makes sense. Our original number was 0.1, and so we're up to 0.15, so that's similar, but bigger. So this is suggesting we need to make a bigger channel constriction. We're going to have lower particle velocity, but a bigger opening so you can get the same volume velocity that you had before. So hopefully that makes sense. That one's a little bit difficult. Easy to miss a step there. But go over this a few times, see if this makes sense for you now. Okay, so proceeding then to number 3. So I say here, in order to achieve turbulent airflow, what is the particle velocity needed for a sound with a cross-sectional area of 0.2 centimeters squared? So in order to achieve turbulent airflow, that's probably suggesting that we're going to need our Reynolds number equation. So as I had it from over here, this is our equation. Now, I said in order to achieve, so actually I'm kind of giving you the Reynolds number value that we're going to need. And so I said, what is the particle velocity needed? So that's going to be our U here. We don't know what that is. That's what we need to solve for. We should be able to get the D from the area given. But we actually already have the Reynolds number as well, because remember that we get turbulent airflow when the Reynolds number is above 1,700. So whatever value you find for U is going to be that or higher, should give you the, which should be enough particle velocity to get frication at that particular size of the channel, the area of the channel. We're really almost there. So you have this. You want to solve for U. Now you don't have the diameter yet, but I gave you the cross-sectional area. So this is where you just use pi r squared equals your area equation, substituting the radius for diameter, which is 2 of r. And anyway, it comes out like this. 2 times the square root of the area divided by pi is your diameter. And when I put in the 0.2 here, the diameter I ended up getting is 0.505 as my diameter, and you should double check that if you plug that back in here. It should give you the area of 0.2 centimeters squared. So with that diameter, I can put that in here into this equation, and I can solve for u. So I'm going to need to multiply this by 0.14 and then divide this by 0.505, and that should give me the u. And yeah. And if you type 0.41 times 1700 divided by 0.505 into your calculator, you should get that the particle velocity needed is 471 centimeters per second. That's actually not really that fast. So yeah, turbulence for cross-sectional area that size does not need to be that particularly high. But of course, that's kind of a big constriction, so maybe it would be kind of hard to maintain that kind of airflow needed. Okay, so 471 centimeters per second is what I get there for number 3. Okay, for the fourth problem here, a speaker clinket with an average sized vocal tract attempts to produce a velar fricative sound. Pressure is built up with constriction of 2 centimeters cubed, and then there's a diameter of 0.03 for the constriction. What is the Reynolds number, and is this a successful fricative? So we're going to need to build towards the Reynolds number equation, and we don't have everything we need for that right now. So we want to see if this is exceeding 1700. So we've been given the diameter, 0.03. We're going to need to find u, the particle velocity. We're going to have to run through a number of equations to get this. So first of all, we have the pressure differential has been, the amount of constriction has been given to us, so 2 centimeters cubed. That's going to tell us how much we change from V1 to V2. So we're going to need to start with Boyle's law here. And we have 1030 here. Well, what else do we even have? So we have to find out what would this area of constriction be for this ejective. Now that's where some people are going to go wrong. So you're going to want to take 3,000. That's the volume of the lungs. But actually you don't need the lungs at all because it's an ejective. Actually all you need, your V1 is going to be 40 cubic centimeters. The volume from the glottis up to the velar constriction. It's fairly small, but and then 2 centimeters squared cubed, of constriction means your V2 is going to be 38 cubic centimeters. So you've actually got everything you need to find P2. Should be 40 times 1030 divided by 38, and you should get a P2 resulting pressure of 1084.2 centimeters H2O. With that, you can then get the particle velocity in our next equation. So U here. Now we need the pressure differential in millimeters H2O. And so the pressure differential, of course, that's going to be the difference from P1 to P2, which should be 54.2, I believe. Now we want millimeters in our equation, so we actually are going to want to put 542 in there, multiply it by 10. And so if you take the square root of 542 times 412, it should give us a particle velocity of 9,591.7 centimeters per second. So from there, we've got our U actually, and so we're basically done. We can finish the problem. 0.03, I gave you the diameter, you don't need to do anything to that. That's in centimeters, times 9,591.7 divided by 0.14. And the resulting Reynolds number that you should get, that I get anyway, is 2,055. And that is in fact above 1,700. So this woman, the Tlingit speaker, was in fact successful in making a sound. So, hopefully that has made sense to you as well, and you can expect to see some problems kind of like this at some point in the future. So, thank you, have a good day, and I'll see you tomorrow. Bye.